In this section, we're going to learn to use the first and second partial derivatives of a function to find critical points and to examine the concavity around those critical points to determine if a point is a maximum or a minimum or neither. And that's kind of a cool situation too. Look at this graph here. I stole it from your textbook. Do you see at this point right here that it's concave down as with respect to y, but it's also concave down with respect to x. I can't make my little pointer go in the back, but you see what I'm talking about. So if you're concave down all around a critical value, that makes that a maximum. Same thing with this minimum. It's concave down all around that critical value, and it is concave down. But this little place right here, it's concave up with respect to those two, leading to those two maximums. But when you look at it this way in between, that's not the case. So let's examine what happens at those points. This picture, you can see that even though you found a critical value right here, it's concave up with respect to one of the variables and concave down with respect to the other. This gives us something called a saddle point. So it's more than just finding the zeros of the first partial derivative and then looking to see if it's a maximum or a minimum based on the second derivative, because everything's mixed up, right? So we're going to do something called a d-test to see if we have a relative maximum, minimum, or a saddle point. Okay, first off, we have to make sure that our function is differentiable in the general area that we're looking at. And let some point AB be such that the first partial with respect to x equals 0 at that point, and the first partial with respect to y equals 0. That makes the point AB a critical point. Now, using the second partial with respect to x and the second with respect to y and the mixed partial, when we plug in that critical point into these values, we get this test value called d. So first we're going to multiply the xx and the yy, and then we're going to square the mixed partial and subtract that. Now, if d is a positive number and the second partial with respect is negative, this means concave down, right? You're at a critical value. This whole thing is positive. But let's talk about what makes d positive. Notice that you're subtracting a square. So this is always going to be subtracted away, right? But if your first partial with respect to x is negative, but d is positive, it means that both of these must have been negative to give you a positive, because you're always going to be subtracting value from that. So if both xx is negative and yy is negative, then about that critical value, you have concave down in that whole general area. So obviously, if d is positive, but the two second partials are negative, you have a relative maximum. Concave down means you're up high, right? If d is positive, but the second partial with respect to x is also positive, that means the yy must be positive. Both of these are pluses. That makes it a relative minimum. Now, if d is negative, then either this part overwhelms this one, or these two guys were opposite signs, and that would make d negative. And if d is negative, we have what's called a saddle point. Okay, let's look at this equation, this function with two variables. We need to find our critical points. Sometimes there are many. By taking the first partial with respect to x, which we already know how to do, and the first partial with respect to y. we are also going to need all of our mixed partials. So xx, taking the derivative of this with respect to x, that's a 0. We just get minus 6x. 2y's is going to give us just a negative 2. So this guy's always negative. The mixed partial, if we take this derivative with respect to y, we're going to get a 2 and a 0. Notice that that's always positive. So finding our critical values involves taking the first partials with respect to x and with respect to y, setting each of them equal to 0, and then solving that system of equations to find all the points that make this system true. So if I start with the first one, notice that 2x and 2y equal each other. Let me write that out here. So this says that 2x equals 2y, or x equals y. So replacing, I know it's still moving, replacing this, this one right here with 2x gives me this. Factor that, set the factors equal to 0. I get 2x values. If x equals 0 and x equals y, I get this point. If x equals 2/3 and x equals y, then I get y equals 2/3. And I have my second critical value. Okay, let's test and find d, which is going to require plugging this point in into the second partial. That makes that a 0. Remember, x is 0 and y is 0. So double x times double y, well, that's just going to give me a 0, minus the mixed partial squared gives me a negative 4. If d is negative, then this point is a saddle point. Okay, using the next point, the 2/3, 2/3, when we plug that into double x, we're going to multiply 6 times 2/3. That's going to give me a negative 4. The second partial with respect to y is negative 2, and then minus 2 squared. So this is going to be positive 8 minus 4 gives me positive number. And the first partial with respect to x twice is negative. So if d is positive and fxx is negative, that makes this concave down and makes it a maximum. Now let's look at a function that has exponentials in it. When we take the first derivative with respect to anything, we're going to copy the e to the power, and then we'll take the derivative of the power. So the derivative of that exponent with respect to x is 2x. First partial with respect to y gives me 2y, because it's the derivative of the exponent there. And the second partial with respect to x is going to make this a product rule. So the derivative of this first factor is 2. Copy the second factor, which is the e, plus copy the first factor, and multiply by the derivative of e to the power with respect to x. That gives us a second 2x. So writing this simplified, I have e to the power times 2 plus 4x squared. Do the same thing now, second time with respect to y. It works the same way. The derivative of the first factor is 2. Copy the second, plus copy the first factor, and then the derivative of e to the power is going to be e to the power times the 2y again. Simplifying that by factoring out the e gives me a 2 plus 4y squared times e to the power. And now the first mixed partial, look at with x. If I take the derivative of this with respect to y, then this is just a constant. So I'm going to copy the 2x, I'm going to copy the e to the power, and I'm going to multiply by the derivative of the power, which is 2y. So that's going to make that 4xy e. Okay, to find our critical values, we're going to set these two first derivatives equal to 0. And e to the power is never 0, so x equals 0 and y equals 0. That's the only critical point. Plugging the 0, 0 into the mixed partials, into the second partials, this is gone, and e to the 0 plus 0 plus 1 is going to give me 2e. Plugging the 0, 0 into the second partial with respect to y, this is going to be e to the 1, and that's going to be just a 2. So those are both the same. The second mixed partial, if I plug in zeros, I just get 0. So D is going to be this number, 2e, times 2e minus 0, which gives me 4e squared, which is positive. E squared, which is positive, and the double x derivative is 2e, which is also positive. That makes this point, it's concave up, and so concave up means that it is a minimum. In this problem, we're working a problem that has a constraint added to it. So this will be a plane in space, and we're operating on this triple function with that constraint. So I isolated the z here. We've only worked with x's and y's. So I isolate the z, plug it in there, and rewrite my function as just being with respect to x and y. So distributing the top and distributing the 2 on the bottom eventually. Then we will simplify the fractions when we can and start taking our derivatives. But sticking this constraint into our regular function means that we will always be on this plane. Okay, let's rewrite this guy. That's 6xy minus x squared y over 2 minus, I already simplified the 3x y squared. So the first partial with respect to x is going to be 6y minus, this brings a 2, which cancels that. I get xy minus 3y squared. With respect to y, we get 6x we get minus x squared over 2 and minus 6xy. Okay, second partial with respect to x gives me a minus y. Second partial with respect to y gives me negative 6x. And the mixed partial, taking the derivative of this with respect to y, gives me 6 minus x and minus 6y. Okay, let's take those two first partial derivatives and look at this system with each of them set equal to 0. This can get complicated, but it's still doable. With the first one, I can factor out a y. So that means either y equals 0 or this piece equals 0. And let's solve for the x. X is going to be 3y minus, 6 minus 3y. So factor in x out of this, write down what's left, solve for one of those variables in terms of the other. I want to solve for x so I can multiply everything by 2 and get rid of that fraction. So solving for x, I have 6x over 2 is 6 minus 6y, multiply away the 2, and we get 12 minus 12y. Okay, now this y can be with this or with this, okay? And this can be with the 0 or with this. So let's take y equals 0 and pair it with this second equation here. Plugging the 0 in here gives me x equals 12. So I have x equals 12, y equals 0, and taking those values, plugging into this right constraint, we can find what z is. So 12 minus nothing gives me nothing, and I get x is 12, running out of room. X is 12, y is 0, and z is 0. Now, let's try the next one. And remember, each of these, we also have to put these together too. So if x equals 0, and I'm using x equals 6 minus 3y, then I can solve for y. And y equals 2. Take x is 0, y is 2, plug it into our constraint. I get 12 minus 12 again. So z is 0 again. I have the point 0, 2, and 0. Now we also have to look at the x is 0 and y is 0 point, and then solve for z. Plugging x is 0 and y is 0 in, I get z equals 6. Up. Forgot to do that. I'll go back and fix that. Look at these two guys right here. We have to solve that system as well. Now if x equals this and x equals this, then this equals this, right? Now isolate the y. So I'm going to add 12 y's to both sides and then subtract 6 from both sides, and I get 9y equals 6 and y equals 2/3. Using that 2/3, plugging it in right here, that's 6 minus 2, which is going to give me 4. So now I have x is 4, y is 2/3, going back up to my constraint and plugging in those values. 12 minus 4, minus 6 times 2/3 is going to be minus 4. So 12 minus 8 is going to be 4 divided by 2. I get z equals 2. And I have the point now. X is 4, y is 2/3, and z is 2. So I have 4 critical values. Now we have to figure out if they are maximums, minimums, or if they're saddle points. And let's go back and fix this guy. Plugging the 0, 0 into our constraint leaves me z equals 12 over 2, which is 6. Okay, 4 critical numbers. So if we're plugging these x, y, and z values into our original function, we're going to get that at this point, my f of x, y, z will equal 0. Plug this in, it's going to equal 0. Plug this in, it's going to equal 0. We're not going to characterize these guys, but when you plug this one in, this times this times this, 16/3, that's going to give us a maximum. And we're going to work this problem again in a later lecture in a way that's a little bit easier. That will take us straight to this value right here. Okay, one more example. Let's find our first partials. First, with respect to x, I'm going to get a y here. Now this guy right here is x to the minus 1, so I get a minus and a square on the bottom. Do the same thing with y. I get x, and this is going to be minus 4 over y squared. Okay, let's set these guys equal to 0 and find our critical points. So y equals 2 over x squared for the first one, and in the second one, x is going to equal 4 over y squared. So I can take one of those and plug it into the other and see what happens. So y equals 2 over 4 over y squared, which is going to give me 16 over y to the 4th, but you're going to flip that bottom fraction and multiply. So y to the 4th comes to the top, 16 is on the bottom, cancels the 2, and gives me y equals y to the 4th over 8, or y to the 4th minus 8y equals 0. Factor it. Y cubed equals 8. Y cubed equals 8 gives me a 2. Thinking way too far ahead here. So I get 2 values of y, so 2 critical points. Plug those 2 values into this right here, and you can get your x's. So y equals 0, that becomes undefined. That's undefined. It's not in the domain of f of x, y. Moving on to y equals 2, and now we're cooking with gas. If y equals 2, plug that in right there. You're going to get x equals 1. So we have the point 1, 2. We need to categorize that as a max or a min. Plugging it in to get its actual value, we're going to get 2 plus 2 over 1 plus 4 over 2. So 2 plus 2 plus 2 gives me 6. So let's check and see if it's a maximum or a minimum or a saddle point. So my second partial with respect to x, this is going to be minus 2 times minus 2, gives it positive 4 over x cubed. Negative 2 times negative 4 is positive 8 over x cubed. And then the mixed partial is just going to be 1. So D, we're going to plug in the 1 and the 2. So XX is 4 over 1. YY is 8 over 8, which is 1, minus 1 squared. I get 4 minus 1 equals 3, which is positive. So if D is positive and double X is positive, that means it's concave up. And it makes that point a minimum. Well, it makes 6 is the minimum value, and it happens at that point.